In previous videos, I derived the definitions of sine of z, cosine of z, and tangent of z in terms of exponential functions, and also the definitions of sine of z and cosine of z in terms of its real and imaginary parts. In this video, I would like to derive a definition of tangent of z in terms of its real and imaginary parts. This requires the use of the definitions of sine of z and cosine of z in terms of its real and imaginary parts, which I established in a previous video, which I will link in the description. It's also worth noting that tangent of z has a restricted domain, and is not defined for z values in the form pi over 2 plus k pi for all integer values of k. To find the definition of tangent of z in terms of its real and imaginary parts, we can rewrite tangent of z as sine of z over cosine of z, then plug in the definitions of sine of z and cosine of z in terms of its real and imaginary parts. Sine of z equals sine of x cosh of y plus I cosine x sinh of y, and cosine z equals cosine x cosh of y minus I sine x sinh of y. So sine of z over cosine of z equals this expression. The next thing we need to do is to multiply both the numerator and denominator by the complex conjugate of the denominator. So we need to multiply both the numerator and denominator by cosine x cosh of y plus I sine x sinh of y. And once we expand both the numerator and denominator, we get this extremely long expression. If we factor sine of x cosine of x from the first and fourth terms in the numerator, we get sine of x cosine of x times cosh squared of y minus sinh squared of y. If we factor out I cosh of y sinh of y from the second and third terms in the numerator, we get I cosh of y sinh of y times sine squared of x plus cosine squared of x. In the numerator, cosh squared of y minus sinh squared of y equals 1. So the first term in the numerator just reduces to sine x cosine x, and sine squared of x plus cosine squared of x in the second term in the numerator equals 1. So the second term just reduces to I cosh of y sinh of y. In the denominator, cosh squared of y can be rewritten as 1 plus sinh squared of y. So the denominator becomes cosine squared of x times 1 plus sinh squared of y plus sine squared of x sinh squared of y. If we expand the first term in the denominator, cosine squared of x times 1 plus sinh squared of y becomes cosine squared of x plus cosine squared of x times sinh squared of y. We can factor cosine squared of x sinh squared of y plus sine squared of x sinh squared of y as sinh squared of y times cosine squared of x plus sine squared of x if we factor out a sinh squared of y from both terms. Since cosine squared of x plus sine squared of x equals 1, this entire expression just simplifies to sine x cosine x plus I cosh of y sinh of y over cosine squared of x plus sinh squared of y. We can rewrite this expression in a different form using a bunch of trigonometric and hyperbolic identities. We can rewrite sine x cosine x as 1/2 sine of 2x using the double angle formula for sine, and we can also rewrite I cosh of y sinh of y as I times 1/2 sinh of 2y using the identity sinh of 2x equals 2 sinh of x cosh of x. In the denominator, we can rewrite cosine squared of x as 1/2 plus 1/2 cosine of 2x using the power-reducing formula for cosine, and we can rewrite sinh squared of y as negative 1/2 plus 1/2 cosh of 2y using another hyperbolic identity. The 1/2 and negative 1/2 in the denominator cancels out, so the denominator just becomes 1/2 cosine of 2x plus 1/2 cosh of 2y. If we multiply both the numerator and denominator by 2, the expression simplifies to sine of 2x plus I sinh of 2y over cosine of 2x plus cosh of 2y. If we separate the expression into its real and imaginary parts, the resulting expression is sine of 2x over cosine 2x plus cosh of 2y plus I times sinh of 2y over cosine 2x plus cosh of 2y. So this is the definition of tangent of z, where z equals x plus iy in terms of its real and imaginary parts. So tangent of z is equal to sine of z over cosine of z, which equals negative I times e to the iz minus e to the negative iz over e to the iz plus e to the negative iz, which is the exponential definition of tangent of z, And this is also equal to sine of 2x over cosine of 2x plus cosh of 2y plus I times sinh of 2y over cosine 2x plus cosh of 2y, which is the definition of tangent of z in terms of its real and imaginary parts. And it's only defined when z is not equal to pi over 2 plus k pi for all integer values of k.